All right, so in this section, we're going to be looking at first-order differential equations that take this form. dy dx equals f of xy. This notation is probably new notation for you, but we use it a lot in Calculus 3. And basically what this is a function of two variables, a function of x and y. So to give you kind of an example of something that takes this form, I could write dy dx equals like x squared y, something like that. You can add a little more to it, maybe sine of xy in there. It doesn't really matter, but the idea is that this thing on the right-hand side here has two variables, the x and the y, and because of that, we think of it as a function of those two variables, x and y. There's a little bit more context there, though, because the fact that there's a dy dx appearing here is implying that y is also a function of x. So even though x and y are variables in their own right, we think of y as a dependent variable, x as an independent variable, so that when we solve, we're solving for y as a function of x. But this is an example of what this is talking about in more general terms. When we have a differential equation that's presented this way, so that the dy dx is isolated, and the equation is a first-order equation, then we think of this function f of xy here as what's called a slope function. And the reason for that is because we can interpret the derivative of y with respect to x as the slope of a tangent line to the curve that we get from graphing y as a function of x. That's from Calculus 1. That's kind of how we define the derivative initially. So the value in this that we're going to see in the example that we do is that you can, even if you don't know how to solve this differential equation, if you don't know how to solve for y here, you can still get useful information out of this differential equation without having a full solution. As we're going to talk about towards the end of this section, that's called taking a qualitative approach to analyzing these DEs. So basically, here's the idea. The solution curve here in blue is part of the graph of y equals f of x, whatever our function is that we're trying to solve for. But generally, we don't know what that curve looks like until we have solved this. So if we're not even going to solve it at all, then we don't really stand a chance of finding this blue curve in its entirety. But instead, what we can do is find the slopes of tangent lines to that curve, which we're not going to see, by using the differential equation explicitly. So for example, if I wanted to find the slope of the tangent line to the solution of this at the point 2, 3, well, 2 is an x value and 3 is a y value, and right here I have a function that takes x's and y's as inputs and outputs the slope of that tangent line there. So I can find that slope without even knowing the curve that we're actually dealing with, okay? So the idea behind what we're going to do here is we're going to take differential equations that are in this form, and we're going to pick a bunch of different points and plug them in to this function right here, the slope function. And the numbers that we get out of that are going to represent slopes at all of these different points. On a graph, which you're going to see in just a moment, we're going to plot little line segments through those points where those line segments have whatever slope we just found. Those little line segments are what we call lineal elements. And if you graph enough of them, it's going to give you a sense of what the curve, the solution curve or solution curves to a differential equation may look like. It's going to provide kind of the directions of those curves. So for that reason, we're going to call the thing that we're about to create here a slope field or a direction field. Okay, so let me go through an example so you can get a better idea of what we're looking at. We have this differential equation dy dx equals 1/2 xy, and we want to create a direction field for it. Now I've already created it here. I used a computer program to do this, but I want to show you how you would come up with these individual lineal elements if you didn't have a computer to do this with. So I'm creating this table here. On the left column, I have x, y, so it's going to be a bunch of sample points that I'm choosing. And these points aren't coming from anywhere specific. I'm just choosing points that have integer values for their x and their y coordinates, and I'm picking some negatives and some positives just to get an idea of what this would look like. In this example, I'm using y equals 1 for all of my y values, that's going to get me kind of just all of the lineal elements along one kind of row of this thing. But let's see what happens if we start trying to find these guys on this right-hand column. So you notice it says dy dx. These are the outputs of this function since it equals dy dx when I plug those points in. So for example, if I plug the point -3, 1 into this function, -3 is the x, y is the 1, so I have 1/2 times -3 times 1, which is -3/2. So what that tells me is that for this function, at the point -3, 1, if that point lies on our solution curve, then it's going to have a slope at that point equal to -3/2. Or in other words, the slope of its tangent line there will be -3/2. So if you were to go over here and look for the point -3, 1, here's -3, here's 1, you notice we have this downhill slope for this lineal element that we've drawn here. The actual slope of that would be -3/2. So I would be careful to make sure that the actual, rise over run, I'm dropping 3 units and moving to the right by 2 units to get this little lineal element there. I'm going to continue filling this out. So you can imagine if we plug -2, 1 into this, that's 1/2 times -2 times 1, which is -1. -2, 1, that point appears here. This tells me that the slope of that lineal element is -1. Downhill, but at a shallower slope than the previous slope that lineal element that I graphed. So you can see how I have a sharper downhill slope here and a shallower one here. We're going to continue doing this. 1/2 times -1 times 1 would be -1/2. And if we go through and fill out the other values in this table, you're going to see 0, 1/2, 1, 3/2. Okay? Those are all using a y coordinate of 1. So that's all the lineal elements that are appearing in this kind of row that I'm seeing here on my graph. But I could get these other values here by looking at the corresponding points, plugging them directly into this function, and seeing what the corresponding slope would be. So the idea behind something like this, again, is to get an idea or a general concept of what a solution curve for this function might look like. It would be a graph that has to have some of these lineal elements as tangent lines, or they would have to be tangent to the graph. So they kind of provide an idea of the direction. On the next page, I'll show you some possible candidates for solution curves for this specific DE. But one thing I do want to point out is that this is not complete by any means. There are points all throughout here that I didn't select, maybe like 0.5, 0.25 or something like that, where I could also find the slopes there. The point of this is not to be complete. It's just to give you some representative lineal elements so that you can work with that. Okay, so let's move on to this page. This is the same slope field, but with a few candidate solutions sketched into it. So if you look at like the lineal elements, if I were to try to graph a possible curve that might act as a solution to this, I'm seeing these horizontal tangent lines all appearing along the y-axis there. That suggests that our solution curve probably has a local minimum or a local maximum there. It may also, that's not a necessity if you have a horizontal tangent. You can have something like a cubic function passing through there, but you would see that a function like that is not going to match up with these other lineal elements very well. If you kind of look at the direction of the surrounding lineal elements here, my curve kind of needs to follow the same direction as those little lineal elements that are close to it. So like this red curve, for example, it only really touches this one horizontal tangent, but it gets kind of close to this guy. This has a downhill slope, so I should be decreasing when I'm near that. In fact, everything, if you look at all the lineal elements in my second quadrant here, they all have negative slopes. So all of my functions, if I have a part of the curve in this quadrant, should be decreasing until they get to the y-axis. And then looking at these guys over here, it looks like it should be increasing out of it. So hopefully you can kind of see where these curves are coming from. None of them are meant to be perfectly exact, but it's just to give us a rough idea of what a solution to this DE might look like if we graphed it. Okay. All right, so here's another example. And this one, we're given another DE, and we're given the direction field for it. So this is the from the differential equation, dy dx equals x over y. But then we have this thing here, this y of 0 equals 1, which is what we call an initial condition. I believe we talked about that in the previous section. But again, an initial condition is a little extra information about your differential equation that allows you to narrow down from a family of solutions, a single solution that satisfies both that differential equation and this right here. So what we want to do is start with that initial condition. This corresponds to the point 0, 1. If y of 0 is equal to 1, then that means the point 0, 1 lies on my solution. So that's right there. There's 0, 1. Okay. Now my curve, which is acting as my solution, if I look at some of these lineal elements here, I know that my curve has to contain that point, and I'm seeing something here kind of similar to what I saw over here, where as I pass through that point, I have decreasing lineal elements, then it goes to increasing one. So I'm expecting kind of a similar curve as one of those. However, I'm also noticing these elements that seem to be sort of aligned along the line y equals x right here. And to me, that sort of suggests that we might have like an asymptote, like a slant asymptote there. So I think that a solution curve for this particular DE with that initial value might look something like this. So I'm not going to cross this line here because I'm thinking of that as an asymptote, but I'm expecting a curve that looks something like that. Okay, so notice it's sort of matching the slopes of the surrounding lineal elements, or at least approximating them. It's not crossing that asymptote, and it does contain this point right here. And because I have a horizontal tangent and I'm decreasing into it and increasing away from it, I'm expecting this local minimum here. So that's a good guess as to what that solution curve would look like. Okay. Now, in the topic of direction fields, it's a good time to introduce this term right here. So if you have a differential equation, dy dx, and it's equal to a function of only y. Remember, on the first page, we said that we were looking at functions or DEs of this type, where dy dx is equal to a function of both x and y. But if there are no x's appearing on this side right here, if I'm only getting y's, then we call this type of differential equation autonomous. So an example of that could be something like this: y double prime minus 5y prime plus 6y equals 0. Okay. These types of second order linear equations where you have these constant coefficients, these show up a lot in lots of different applications. You spend a good amount of time studying these specifically in a differential equations class. But this is autonomous because there's only y's and y primes showing up in here. Now this, I should actually use a different example because this is a second order one, and here we have a first order equation. So let me actually use a different example. Let's try something like, I want to put it in that form too. Let's say like dy dx equals 5y, I don't know, plus maybe like cosine of y. So that's another example of an autonomous DE because there's only y's appearing here, no x's. So for us, we're using the term autonomous strictly for like the first order case of a DE. And these have an interesting property when you start looking at their direction fields. So if you think about that, dy dx is equal to whatever the output of this function is, but the output of this function only depends on y. It's independent of x. So what that means is if we fix a y value, if I plug a specific value in for y, then I'm going to get the same slope regardless of the choice of x that I plug into that. So here's an example of a slope field for an autonomous differential equation. If you pick any row of lineal elements, you'll see that in each row, all of the lineal elements look identical. So here they're all horizontal. Here they all have they have the same negative slope. And the reason for that is because on any horizontal line in the plane, you have a fixed y value, but you have varying x values. And according to this, those different x values won't change whatever that slope is if you fix your y. So this is something that happens with autonomous differential equations in not an application, but an implication of that is that if you have any solution curve for one of these guys, then any translation to the left or to the right, so any horizontal translation of that solution curve is also a solution to that differential equation. So here you have this red curve here, but because all of these lineal elements are the same as we go from left to right, we can translate this curve anywhere we want to the right or to the left, but we're only looking at ones to the right here. And those solution curves will also follow the direction of those lineal elements. So that's a useful property when solving things like this, because if you know one solution, then you can get an infinite family of solutions just by shifting it to the left or to the right. Okay? We're going to move on from here to talking about Euler's method, and I think I'm going to use the next video for that.